session Symmetric I. We're moving everything by 5 minutes, so we're starting this session 5 minutes late, and we'll end at 12:05. The first talk, which will be given by Kosei Sakamoto, is entitled Ether, an ultra-high throughput and low-energy authenticated encryption scheme. Kosei, the floor is yours.
Thank you for the introduction.
Can we load the slides?
Okay. Yeah. So this is joint work with Spadi Panik, Andrea Caforio, Tatsuya Ishikawa, Takanori Isobe, Mustafa Izarama, and me, Kosei Sakamoto. So here is the contents of my talk. So first, I will explain the background of our works. So the data center faces the demand for ultra-high-speed data processing. So actually, in the rapid growth of data consumption requires unprecedented processing speeds in data centers. And so cloud store data is projected to reach 100 zettabytes by 2025. And moreover, terabit per second encryption speeds are necessary for 6G and beyond 5G. And also, there is a roaming energy problem for the data centers. So data center could consume 1,000 terawatt hours by 2026. So the European Union's Energy Efficiency Directive imposes new obligations on operators, which include emissions reporting for any data center larger than 500 kilowatts. And also the United States Department of Energy stresses developing energy efficient technologies for data centers to reduce environmental impact. Concerning this situation, encryption schemes must be performed not only at high throughput, but also with low energy encryption, energy consumption. So as the previous work, there are several works for low energy encryption schemes. So in general, energy consumption in cryptographic circuit is characterized by the total switching activities. So that is the number of 0 to 1 transition of the logical elements. And so maybe there is some way to optimize energy consumption. And the first one is the high throughput AES-based AEAD, like AES-256 and LogS. So they can proceed large data chunks in a few clock cycles, and which contribute to the achieve the impressive performance. So in fact, this AES-256 and LogS is designed for software, but they also achieve a very good high throughput even in the hardware. But for energy consumption, they duplicate AES-RAND function in parallel, which increase the energy consumption. So as another approach, Stream Cipher are considered to be a very good choice for the low energy encryption schemes. But it struggles to reach terabit per second. So our research question is, how can we design a high throughput AED with small energy consumption? I will explain our strategy. So to this end, we revisit the high throughput AES-based AEDs, like AES-256 and LogS. So we replace the AES-RAND function in the round update function with another low energy inner function. And then we redesign the round update function from scratch. By this strategy, we propose a new authenticated encryption scheme named Ether, which is optimized for both throughput and energy consumption. So Ether is based on edge-like structure as shown in this figure. So for performance, the throughput, the Ether can achieve over 2 terabps in hardware. And also, so Ether so achieves the lowest energy among edges like AEs and the other important cryptographic. For security, Ether claims 256-bit security against key recovery and 128-bit security against forgery attacks. Next, so I will briefly explain the specification of Ether. So as can be in the previous slide, so Ether is based on the aegis-like structure with roundup function R. The interface is Ether accept 128-bit nonce and 256-bit keys, and so output 128-bit tags. And so similar to the other AES-based aegis-like AEDs, so Ether consists of 4 phases: initialization, associated data processing, encryption, and finalization phases. And the roundup function R, so as shown in the below figures, can be applied to R in the upper figures. This is the specification of the internal function. So internal function F is optimized for low latency and low energy, so which is based on SPN construction and consists of a 4-bit box S from Orthoros, 60 by 60 binary matrix proposed by Akure Karaku et al. For the claim security, so as I explained before, so Ether claims 256 security against key recovery and 128 security against distinguishing and forgery attacks. And also, so we set limitation for a fixed key. So the length of associated data is allowed to up to 2 to the power of 128, and the length of message allowed to up to the power of 64. And the number of different messages is also limited to up to the power of 128. And we do not claim any security for the key committing. So because aegis-like AEDs are inherently hard to ensure this type of security, as shown in these works. Okay, next, so I will explain the design rationale of the Ether. As the existing works, so there are many existing works for low energy and high speed. So for low energy, it is considered to suitable. The stream cipher is considered to suitable for low energy consumption. So because they can produce multiple key stream bits per cycle, so which is very good for energy. But they are not optimized for high throughput and also not provide post-quantum security. So for high throughput scheme, so aegis-like AEDs can achieve impressive throughput in software. So although they are designed for the software, they are also can achieve very good throughput around 1 Tbps, even in hardware. And also they provide post-quantum security, but they are not optimized for the low energy. So therefore, so we set our goals to optimize aegis-like AEDs for low energy consumption. Okay, so in this work, so we revisit aegis-like structures. So aegis-like structure is based on a sponge-like construction with a lightweight round update functions. So, normal aegis-like AEDs, so such as Aegis 256 and Locker, so they can apply AS round function in their round update functions. And as you can see, so to enhance the throughput, the very straightforward way is to reduce the latency of the round update functions. And energy is closely related to the circuit area and the latency. So the reducing latency is also contributed to the improving the energy consumption. So we try to replace the AES round function with another small delay function. So we try to design a small delay function. Okay, so as a general construction of the small delay functions, so we select a SPN-based construction because many low latency primitives is based on the SPN. And the performance requirements, so we have two performance requirements. The first one is at least the small delay function can achieve smaller delay than the AES round function. So similar to these requirements, a small area is preferable if possible. For the security, so we set it to the AES like AES must prevent internal collision-based forgery. But so it depends on the construction of the round update function. So it's difficult to evaluate only by the small delay function. So we set the security requirements of the small delay function as the maximum differential characteristic probability over two cascaded small delay function must be less than 2 to the power minus 13. So which is the same as the AES round function. Okay, so then we try to design S-box in the small delay function. As I mentioned before, so there are many works about the low latency primitives. So we decided to select the S-box from these low latency primitives. So based on our evaluations, the 4-bit S-box have a good balance between security and implementation cost. And so among them, so the S-box from Ortoros is looks the best choice for our scheme. So because they have the optimal security property and the good delay and small energy consumption. Okay, next, so we have to select a linear layer. So here, we try to select a matrix. So in several low latency primitives, so almost immediate matrix is used in them. So because the almost immediate matrix can provide a good security and can be implemented by very small area. But so in small delay functions, so it is essential to ensure as smaller maximum DHCP as possible on a few non-linear and linear layers to achieve a small delay. So considering it, so we consider a binary matrix with a stronger diffusion property while minimizing overhead. So we try to we investigate the 8 by 8, 60 by 60, and 32 by 32 binary matrices as a candidate. So they can have a good branch number compared to the almost immediate matrix. And as our evaluations, so these three matrices is good for both security and implementation cost. So we select these three matrices as a candidate. So we we have three structures of the a candidate of a small delay function. The first one is the Ortoros S-box with 8 by 8 matrix. And the second one is Ortoros S-box with 60 by 60 matrix. And the last one is Ortoros S-box with 32 by 32 matrix. And so we evaluate the minimum DCP of these functions and implemented them in hardware. So as a result, so we found 1.5 round of F60, so which is a process box 60 by 60 binary matrix looks best choice in terms of both security and implementation cost. So we select 1.5 round of F60 as a small delay function. This is the overview of our small delay function. So it consists of 4-bit S box from Ortoros and 60 by 60 binary matrix. For delay, so it is 21% lower than the AS round function, and for energy, so for energy consumption, it is 60% lower than the AS round function. Okay, so next, so we need to redesign the round update function. Also, we do not use the AS round function, so we have to design a new round update function. So as a difference in the throughput between software and hardware environments, so in software, so the number of AS rounds is related to the throughput of the whole function. But in hardware, so we can execute AS round function or a small delay function in fully parallel. So we do not need to, we can apply these functions to the all 128-bit states. It can contribute to the enhanced security. Okay, so for design low energy encryption scheme, we need to minimize the delay and the size of the area. And for delay, so it's already done by the small delay function. And for area, so it can be achieved by reducing the number of applied small delay function. But it could weaken the security. So instead, we increase the number of messages in the round update functions. Okay, so this is the requirements for the round update function. So for performance, so absorb as many message blocks as possible. And so keep the number of state words small. For security, so achieves 128-bit forgery resistance, which is the same as Aegis like Aegis 255, Shaoxing, and Rocker. Okay, then so we have to find the optimal round update function. So we evaluate the security against internal collision-based forgery by SAT, and evaluate worldwide truncated differential characteristics. Since so our small delay function can achieve 2 to minus 16 DCP, so it is enough to have 8 active small delay functions to resist forgery attacks. And so we try to search this construction and find the number of state is 9, and the number of inserted messages is 3 is the best choice for our AADs. Okay, so next I will briefly explain the security evaluation. So this is just a summary of our security evaluation. So we conduct the security evaluation for these attacks. And so we confirm, so there's enough margin, there is enough security margin against these attacks. Okay, next. So I will show the hardware evaluation. So for SBox implementation, so there are several ways to optimize these implementations. So we try to 4 patterns of the implementation of the AES. So as a result, the ATEL achieves the highest throughput and the lowest energy among these AED schemes. Okay, so this is a summary of my talk. Thank you so much.
Let's thank Kosei. Please line up behind the microphone if you have questions. I think we have at least one question.
So what I understand you to have done is you took AES, I'm sorry, AES as a starting point and optimized it for low energy and throughput. Why not start with ASCON instead? Because that would already be lower power. And why did you start with AES instead of ASCON, I guess is my question.
Because this edge-like structure can achieve the good throughput than ASCON. So we need to achieve a good throughput and a small energy consumption. Of course, ASCON is the best choice, but edge-like structure is better than ASCON in terms of the throughput.
Right, but if you put the same effort to optimize ASCON's architecture, anyway, it's a hypothetical. If you could have done better with ASCON as a starting point instead of AES.
Yeah, I think ASCON is a lightweight. Okay. No, it's a good question, right? But ASCON is designed for lightweight applications, so they're your resource constrained. And here the focus is on high throughput,
right.
high data center applications. So then you have a completely different set of parameters
Right.
that you're optimizing. And I think I think this is shown in the diagram as well, that you get better throughput from an AES-based design. Okay, we actually have a bit more time for questions. Are there still more questions in the audience? Otherwise, I will ask. Yeah, please line up behind the microphone.
Have you checked the software performance as well? Because as far as I know, some of the hardware optimized schemes, they are not so well in the software.
Yeah, actually, so we evaluate the software, evaluating software. So maybe I guess ATEL is not good for softwares.
Okay. Are there changes you might make to the design to make it better for software? Have you thought about this?
I think so. It's difficult to. It's difficult if we take this strategy. So if you want to optimize the software environment, so we need to take completely another strategy.
Okay. We still have time for one more question, if there might be one from the audience. Okay, then let's thank Kosei again. Thank you, Kosei. So the next talk will be given by Wonsok Che and is entitled Kimrick, Short-Tailed but Mighty, Beyond Birthday-Bound Secure Authenticated Encryption for Short Inputs. Let's welcome Wonsok.
Thank you, Nicky, for introducing me. So yes, I'm going to talk about our new paper, Symmetric I, but Mighty. This is a collaborative work with many wonderful researchers. Let's start with, so what is Kimlik? So Kimlik is, those are examples of Kimliks. It looks nice, right? So for detail, so let me explain about the detail of the Kimlik, what is Kimlik is. So Kimlik is a Canadian cat breed, and this is also called the long-hair Manx. And then probably if you follow my presentation well, then you will probably have one more question. I think the question is, what is Manx, right? So let's see what is Manx is. So Manx is an encryption mode presented by Alexander Kaziko and Junji in SCTRSA 23. So basically this Manx takes a very short length message input and output the ciphertext. Together, this text is included in this ciphertext. So it also has two modes. So if message is a bit longer, then it may use a two block cipher, say AES, or otherwise it can process by just only one block cipher. So here now we know what is Kimnegis and what is Manx. Our observation is Kimnegis cuter. It has a longer hair, which is nice. So definitely at this moment we decided to focus more on Kimnig instead of Manx. So let's see more details. What is Kimnig is? It's a BBB secure AEAD dedicated to short input. Personally, I like the part of how we proved its security. We even show this construction achieve a certain level of tightness by showing some kind of impossibility proof. And it is, of course, super fast. It's cat, so why not? So this is the Kimnig, short tail but mighty and hairy one. So the motivation of this work is this. There are many low power wireless communication, and it has limited packet length, and some power constraints are there. There are so many examples. I would not want to read all of them, but if you want to see more detail, you may check other papers, explain those examples. And let me explain some more technical things. Let's start with some more techniques. So basically what symmetric crypto provides is, the first one is privacy. You can use encryption mode to output ciphertext. And the second one is authenticity. You can use MAC to authenticate your data. And even can both. So in general, we want to using authenticate encryption to ensure your privacy and authenticity. Like for example, like you use GCM mostly because it is standardized. This is a generic AED, so it's not very efficient in dedicated special purpose. So one example is this. Even for encrypting 1-bit information, if you want to achieve a beyond birthday bound security, you require at least 2 block cipher call, because ciphertext should be random by the definition of semantic security. And because of PRP-PRF switch, if you use a block cipher, it is essentially a PRP construction, and for security, for like semantic security, you need a uniform random property, which is only birthday bound secure if you're using PRP. And for even when you want to operate MAC, it is also required 2 block cipher call if you want to achieve a beyond birthday bound security. The opposite example is like Wegman Carter soup and hashdem encrypt, both MAC construction using only 1 block cipher, but limited to the birthday bound security. So what is beyond birthday bound security then? So let's start with the security of nonce-based AED. Because basically, when we analyze the security of AED construction, we consider 2 security notions, the privacy and authenticity. So we assume in the real world, adversary interact with 2 oracles, which we call encryption oracle and decryption oracle, while in the ideal world, this encryption should be totally random, while we assume you should not be able to decrypt. Adversary can't decrypt, so this oracle in the ideal world, it only returns both. And we define the advantage of an adversary by the winning probability of the adversary after making a certain number of queries. So we denote QE and QD for the number of queries adversary makes before making a decision. And the birthday bound means your adversarial advantage of the NAEA security of a given construction by making QE and QD query. If this is bounded by a big O of like q square by 2 to the n, then we call it a birthday bound security. In practice, we want to make this advantage small enough, even you make enough number of query. Say, if you want to maintain the adversary advantage is smaller than 2 to the minus 64, then you should rekey once you make 2 to the 32 number of queries because of this bound. And this is even worse if the bound is in terms of number of blocks of call instead of number of query you made. So, and actually, this is a typical case when you operate the authenticated encryption mode. Normally, the advantage bound, including like GCM or OCB or GCM SIV, almost all standardized AAD, they have a birthday bound in terms of number of block cipher calls. And there are some examples of BBB secure construction. Let's say EK and EK prime are keyed block cipher, and N is a nonce. So nonce is the number without repetition. So whenever you make an encryption query, you want to use a distinct nonce. And in this presentation, N can be N bit or N-1 or N-2 because I'm a bit late to modify those notations. And we also assume an almost XOR universal hash. So one popular example is sum of permutation construction, also PRF, but you can use it as a like counter mode instantiation. So basically, sum of permutation is simple. You just XOR evaluation of 2 block cipher. In this way, you can make almost truly random key stream. And by XORing plain text, you can obtain ciphertext. So this can be a mode of operation for encryption mode. And for MEG, there is so-called encrypt Wegman-Carter with Davis-Meyer. We call EWCDM, proposed by Cogliatti and Surin in Crypto 16. In this construction, the tag is computed by encrypted nonce, XOR with a nonce, and the hash of the plain text. And then you encrypt again for this entire value. So our starting point is how can we obtain a better AEAD in short message? So one way is amalgamating EWCDM, nonce-based MEG, and SOP-PRF because both provide BBB security. And the more good thing is very recently EWCDM MEG has been analyzed via improved mirror theory. It was presented in last Asia Crypt. So one easiest approach is you just can generically compose EWCDM SOP, which is proven to be secure. But if you just composing them in naive way, then you require more key material, also more block cipher call, which it's generic composition, which obviously does not guarantee your optimality. So instead, we introduce a Kimnik family. So left is a cat, and right is an algorithm. Both are Kimnik, but we call it Kimnik 1 if you're using n concat m to XOR this wire. And we call Kimnik 2 if you're using just m to XOR this wire. So basically, this construction compute the sum of 2 permutation by inserting nonce and associated data, and then using SOP construction to make a block encryption mode, also stream cipher, and then you encrypt again, similar to EWCDM, to obtain a tag. And security, we achieve this level of security is actually an optimal security. We believe you cannot do better than this for Kimnik 1 if you add nonce and message together to this wire. If message is a little bit longer, so it might be possible you cannot append nonce and message together in this n-bit wire. Even in this case, you can obtain this level of security, which can achieve a 2n by 3-bit security. So to explain how did we prove this security of Kimlik constructions, we introduced another oracle, the head inc, which outputs a tag without truncation for encryption query. And then we define a variant of real world, which we call an intermediate world, using the similar notion. So the intermediate world uses a random function, but it output a full length of tag before truncation. So, and this random oracle has more interesting property, which is not a typical random oracle, which just return the random value uniformly chosen. Here, this random oracle chooses the tag value uniformly random, but without replacement, only if message is the same. So by dedicatedly choosing this kind of special intermediate world, we were able to prove this rear, and head inter can be bound by some level kind of optimal security bound. While obviously both this intermediate world and ideal world, basically both are in idealized setting. So those oracles just return the random value, but this one without repetition, and this one may be able to do repetition. So the change is just a typical security of truncated random permutation, which achieves this. I will not explain the detail how to prove this, but when we want to prove the distance between the real and the intermediate world, we define some bad events and analyze the probability of obtaining these bad events in the ideal world. For example, if there are multiple tag collision or some bad events, it cannot be possible, it cannot be happen in the real world. So basically, we define a bad event if it is the real bad, which means it cannot be happen in the real world, or just for technical reason. I will explain about what is mirror theory. And then after you ruling out those bad events, what you can do is applying mirror theory for all good candidates. And let me just briefly introduce what is mirror theory is, because I'm addicted in these things. So this is proposed by Patarin, and basically this is just like counting method, how to lower bound the number of some specific systems, the solution to a specific system. So let the P1 to PQ and Q1 to Q2, QQ is an unknown variable, and Z1 to ZQ is a prefixed constant. And we define a sigma as a system having this number of equations. So to prove our construction, we have to count the number of solutions, count the possible P and Q candidates as precise as possible, and mirror theory can do this. If you think if this P1 and Q1 just assign randomly, so in roughly saying, whenever pick the value of Pi and Qi in random way, you obtain this probability satisfying one equation is approximately 1/2 to the n. And actually, the number of choice, if you think this because P1 and Q1 are from the permutation, so it cannot be the same. So the number of choice of those two permutation is close to this formula. Yes. So how to solve this, how to count the number of solutions to this system is by drawing a simple graph. And we define a graph, something like this. And the Cauchy max implies the maximum size of a connected component. So because we have to bound this size of connected components to apply mirror theory, we define an additional bad event to allow us to use mirror theory. So yeah, that's all for difficult details. And let's go with more fun part. So another interesting work thing is we actually show the optimality of Kimlik 2 in terms of number of block cipher call and also additional assumption with no costly operation. To argue our optimality, we define a generic construction which we call GAE for a short input AE that possibly use linear operation and 2 block cipher call. So we just define the very generic construction taking nonce and message and arbitrary linear operation to be an input to the first block cipher, and then again operate something to be a second input to the second block cipher, and finally you get the ciphertext and tag. And somewhat surprisingly, we were able to show when tag is n-bit, there is a birthday bound attack. So it means that you cannot construct the better construction you cannot construct better AEAD mode using 2 block cipher, achieving more than birthday bound security. And even for tag construction, which is a little bit more trickier, but you still can do a birthday bound attack for this case. So how to do this? This is surprisingly simple, so let me explain this. So without loss of generality, we assume the ciphertext and tag is the linear summation of the W, what is this output of the first block cipher, and Y, which is the output of the second block cipher, because we can rule out nonce and message anyway if you know the algorithm. And then we consider the rank of this given matrix. If this rank is smaller, then you just be able to find you just can compute X by letting C equal the X times C equal T. And even this rank is 2, if you can find a collision in V as the input of the first block, then it directly implies the collision of W, and which allow computing by computing C and T. So this is the most tricky part. Sorry, I think it doesn't work. Let's just go on. So even if you were not able to find any input collision, say it is possible if you using only nonce for the first block cipher call, it might be possible. Still, you can make a birthday number of QE queries, and then you still can try to find some, try to find a nice collision to solve this equation. So even for this case, you are able to find a nice to pair to solve this equation, which ultimately allow you to distinguish this world and truly random ideal world. And for tag, if you truncate a tag, this approach cannot directly apply, but still it is possible. I will not explain in this talk, but you may be able to find how we did it by seeing our paper. So maybe you are mostly interested in, so what is the result? What is the performance of our construction? So the above 4 are a generic construction that can take almost any message length, but you can see the minimum number of block cipher call is huge while the security is birthday bound. The only exception is XOCB, which can achieve a BBB security, but it requires the 9 block cipher call even you want to encrypt just only 1 bit. To compare with that, ETE and Manx2 are formally known the short length dedicated AE. They can achieve AE security with less block cipher call than us, but their security is bounded by n-half. And our constructions even can take sometimes more message length than, for example, ETE. And we use a little bit of weaker assumption on our block cipher. We only need PRP security for block cipher. We're using a 3 block cipher core instead of 1 or 2, but By doing so, we achieve optimal security or BBB security. And notably, our construction had no ciphertext extension, while the previous two dedicated construction has a ciphertext extension. And this is a performance evaluation for our construction in some platform. Actually, I didn't do that. I can't explain this part. So if you have a question in this performance metrics, you should drop an email to my collaborator, Alexander, for more information for performance part. So yeah, we also implement and benchmark and did something. I can't explain, sorry. And when we're using a computed round key, I mean, for most cases, what I can say is our Kimnig is much better than other candidates. So this is the last slide of my talk. We use nice intermediate word to show an optimality of our construction, which return the tag by choosing uniform random but without replacement. And we also provide a lower bound for constructing encryption modes, max, and AAD, which can be, I think personally, it is very interesting to think more about the more impossible result and what is the lower bound of what we can do when we design the mode, the max, AAD. Because so far, I couldn't see any relevant literature discussing this kind of problem. So thank you for listening. This is the end of my talk. Thank you, Nicky, again.
Thank you, Won-Sok. We have time for questions. Please line up behind the microphone if you have a question. And I heard Won-Sok likes a lot of questions about the implementation part. That's what you said. Yeah, please.
Thank you for your good presentation. As far as I know, there are many non-misuse cases.
Yes.
How about your scheme?
So our scheme provides a non-misuse response for authenticity. So actually, even you misuse nonce, it is still secure in terms of authenticity up to birthday bound. But because we use a counter mode is essentially not entirely non-misuse insecure. So because you just XOR the message. So if you just, for example, you XOR the 1111 bit to your ciphertext, you immediately can recognize this. The message is just like you can decrypt the same message but XOR 1111. So you cannot avoid this if you want to use this parallel style construction. Thank you.
So I have a small follow-up question on this, Won-Sok.
Yes.
So when you say nonce-misuse resistant for authenticity, what exactly do you mean by that? Because of course, if the nonce is reused, you know the tag.
Yes, exactly. Even if you nonce was misused, so adversary can know like few result, you can call it nonce and message to get a ciphertext and tag, even if you misuse the nonce. But from this information, you are not allowed to forge the new nonce, the C and T pair to get a new N and M pair.
Okay, yeah, thank you. Let's thank Won-Sok again for the great presentation.
Thanks.
Okay. Then we move to the... The organizer already prepared for the last talk to go over time. Let's hope it's not necessary. Let's move to the last talk given by Yongjin Jean, entitled A Framework for Generating S-Box Circuits with Boyer-Peralta Algorithm-Based Heuristics and its application to AES, Snow3G, and Saturnin. So, Yongjin, the floor is yours.
Thank you for the introduction. My name is Yongjin Jeon, and I'm a a PhD student in the defense laboratory of Korean University in Korea. Today, I'm going to this paper, present this paper. On behalf of my co-authors, Seung-Jun Baek, Gi-Yoon Kim, Jong-Sung Kim, I am pleased to present our work. First, I will begin with an introduction. Then I will discuss the BP-based heuristic and expand how we extend it. I explained. Yeah. After that, I will introduce our framework and present the experimental process and the results. Finally, we conclude and suggest future work. Today, we see a growing number of devices with very limited resources, such as those used in IoT network. From this perspective, the cryptographic community can take two approaches, either designing new lightweight ciphers or optimizing existing ones. If we design a new lightweight cipher, the overall network can become more efficient. However, it usually requires a significant cost before a standard is established and the cipher is widely deployed. On the other hand, if we optimize existing ciphers, we can improve efficiency at a relatively low cost while still maintaining compatibility with existing devices. Our researchers focuses on the latter approach. There are several factors that define what we mean by lightweight. This includes latency, area, memory, power, and so on. In our work, we focus on latency and area. From a circuit perspective, we evaluate these properties by measuring the depth and the gate count, which serve as indicators of circuit performance. Our tool also focuses on the S-boxes. There already exist several automated tools for S-box optimization, such as lighter, pagan, set-solver-based tools, and graph-based A-star search tools. These tools are quite useful since they can handle a wide range of operators. However, they face limitations when it comes to implementing large and complex S-boxes, such as AES S-box. There has also been extensive research on optimizing circuits for linear layers. Among these studies are BP-based heuristics, such as BP, RMBP, and BP with limit depth ACT. In addition, there are tools based on matrix decomposition and backward search ACT. The advantage of these approaches is that they can optimize even large matrices, such as 32-bit AES mixed column matrix. Naturally, these tools cannot be applied to circuits with operators other than XOR gates, as they are intended for linear layers. At this point, we propose a key idea. If a linear layer circuit optimization algorithm can be extended to handle nonlinear operators, then it should be able to optimize circuits for large S-boxes, such as the AES S-box. In this work, we focus on BP-based heuristics and extend them accordingly. In conclusion, we have succeeded. Our extended algorithm works effectively for both the 8-bit AES S-box and the 16-bit serotonin super S-box. In previous studies, researchers had to divide large S-box circuits into smaller S-boxes and linear S-boxes, linear layers, and then optimize them separately. However, with our algorithm, we can optimize all of the linear gates in the circuit at once. This means that we can take into account more room for optimization within the circuit. We also compared our algorithms with existing optimization tools. Unlike other approaches, our algorithm requires the full S-box circuit as input, but in return, it can be directly applied to the AES S-box circuit itself. Here, we present new results on AES S-box circuits. Excluding the result by Hazik and Blum in the same CHES issue, the minimum depth of AES circuits have been 15. We reduced the gate count at these steps from 161 and 134. In addition, the lowest known gate count for AES box circuits so far was 113. At the gate count, we further reduced the depth from 27 to 26. Now let me explain the BP-based heuristic. It was developed by Boyer and Peralta for optimizing the AES mixed column circuit. They proposed this algorithm to reduce the XOR gate count in linear layer circuits. Over time, many variants have been developed, including RMBP and BP with a depth limit. The algorithm operates in a way similar to a state machine. It repeatedly updates the current state for the base according to a given strategy. Each update adds a new XOR gate to the base. Once all output values called the targets are included in the base, the algorithm terminates. There are many variants and strategies, but there is one concept through all variants is a distance. Distance between base and target is defined by the minimum number of XOR gates to construct the one target. In the case of variants with a depth limit, only XOR gates within the given depths are considered. The base is initialized with the circuit inputs x0, x1 dots, xn minus 1. When a linear layer is given, it is converted into matrix form to define the targets. This matrix form can be understood as extracting XOR information. For example, the distance between the initial base and y0 is 1, while the distance for y2 is 3. A commonly used strategy in BP-based heuristics is the preemptive strategy. This strategy immediately implements any target whose distance 1 without further search. In the example, since y0 can be constructed by x0 XOR x1, the algorithm immediately chooses x0 XOR x1 and adds it to the base. Because this algorithm is designed for linear layers, it does not work if nonlinear operators are present. We extend BP-based heuristics so that they can handle nonlinear operators. Our work builds on the previous heuristics, which extract XOR information from linear layers. We cannot obtain the necessary operator information from an S-box table. So we use the S-box circuit itself as the input. The example on the right shows the gift S-box circuit. In our approach, the inputs of nonlinear gates are also as targets. We further modify the strategy to add nonlinear operators to the base, but only in a limited way. If a target requires nonlinear operator that is not in the base, its distance is set to infinity. We call our new strategy the new preemptive. It is very simple. If two inputs of a nonlinear gate are in the base, then we immediately add the output of the gate to the base. For example, in the gift S-box circuit, G0 is constructed by an AND gate of X0 and X2, and they are in the base. Then it is selected right away. The new preemptive is applied before the original preemptive. This is our algorithm. The black text is the original BP-based heuristic, and the red part is the added part. It works well. But our extended BP-based heuristics also have a limitation. The results of algorithm heavily depend on the given circuit. To overcome this limitation, we propose a framework. This idea is to add diversity by rewriting the given input circuit. This framework consists of 3 steps: pre-processing, optimizing, and post-processing. During the pre-processing step, we generate diverse circuits through equivalent circuit transformations. Since our algorithm does not handle NOT gates, we separate and store them at this stage. In the optimizing step, the extended BP-based heuristic is applied. After optimization, in the post-processing step, we reinsert the stored NOT gate to construct the final circuit. Finally, we select the best result among the candidates. I will explain how we rewrite the given circuit in the pre-processing step. In the step, we use the properties of nonlinear gates and XOR gates. Even with just AND gates and OR gates, we can rewrite various equivalent circuit by leveraging XOR gates. However, when there are many nonlinear gates, it is not feasible to examine or possible transformations. Therefore, we apply a greedy search to find transformations that reduce the largest number of XOR gates based on extracted XOR information. Now, let me describe the circuits used in our experiments. The representative target ASS box circuit is usually implemented with a tower field construction, and the choice of bases allows for different implementations. These 2 figures show circuits implemented with a normal basis and with a polynomial basis. Here, IMV refers to the inverse function over GF to power 4, which is treated as a 4-bit S-box. We use the tool from JBK24 to re-implement this 4-bit S-box and construct diverse AES box circuits. In addition, several other AES box circuits have been proposed in the literature. We also carried out experiments on the Snow 3G S-box. The Snow 3G S-box uses the finite field function G49, which can be computed as a repeated composition of G7. The circuit for G7 is shown in this figure. In our implementation, we treated squaring and multiplication as field operations, while the 5th power operation was optimized using the tool from JBK24. As a result, we achieved a circuit with only 456 gates compared to the previous 498 gates. Since the Snow 3G S-box circuit has a large number of gates, full optimization was too slow. Therefore, in our experiments, we optimized the G7 and then concatenated it to build the G49. Saturnin uses a 16-bit Super S-Box, which consists of 8 4-bit S-Boxes combined with an MDS code. Following the implementation described in the Saturnin proposal, the total gate count is 134. We extended RMBP and BPD from the BP-based heuristics to develop eRMBP and eBPD, and conducted our experiments using them. In our experiments, our tool discovered circuits with smaller depths than the original circuits. At the same time, the XOR gate count also increased. Thus, we are able to observe the trade-off between depth and XOR gate count. As mentioned earlier, we also achieved new records for the AES box. For the Snow strategy and the Saturnin S-box circuits, we reduced the depths by 10 and 3, respectively. To conclude, we developed a framework for optimizing large S-boxes as a whole. In doing so, we designed and applied extended BP-based heuristics capable of handling nonlinear gates. We showed the efficiency of our approach through representative applications to the S-boxes of AES, Snow 3G, and Saturnin. For future work, we see two main directions. First, eBPD sometimes generates duplicate gates for the same value, and removing them would improve performance. Second, since our extended algorithm inherits the properties of BP-based heuristics, employing other improved variants could lead to even better results. In summary, our algorithms and results demonstrate that large S-box circuits can indeed be managed holistically. Here is a reference. Thank you for listening to the presentation. Thank you.
Let's thank Youngjin. It's a bit of time for questions. Are there questions from the audience? Yes, can you please line up?
Thanks for your nice presentation. I have a little question. That is, what about the performance of your BDP?
BPD?
BPD algorithms?
Yes.
Have you met some case when the runtime of the algorithm is too long, so you have to abort it?
Long algorithm? Long time?
Long time, yeah.
Yes. How long time?
Yeah.
Yes. The speed this algorithm is proportional to the maximum distance.
Maximum.
Yeah. In simply, it is proportional to the number of linear gates in the resulting circuit. Yeah. So with our Python tools, the AES box typically takes 1 hour with eRMBP and sometimes 6 hours with eBPD. Yes.
Okay, thank you.
Yeah, thank you.
I have a small follow-up question about this.
Yes.
So you mentioned 1 hour or 6 hours. Like, what are you using? Some standard laptop or some cluster? What hardware? The
yes,
hardware.
it is computer, personal computer. Yeah. So it but it use only 1 core, so
Okay.
it can do multiplication, but multi-core. Yeah, it can. Yeah.
Okay.
Yes.
Thank you. Let's thank Youngjin again for a great presentation.
Thank you very much.